have you ever stopped to wonder what's really happening inside a piece of steel when it bends? I mean, it looks simple enough, but deep down there's an invisible force at work, a secret that explains pretty much everything from car crashes to airplanes. So let's go ahead and unlock that secret. So here's the big puzzle that gets us started. If you take a metal rod and pull it straight apart, you'd think it would just stretch and then snap right in the middle, wouldn't you? But weirdly enough, that's not what happens. Why on earth does it deform on this strange diagonal angle?
And this image, well, it shows you the puzzle perfectly. The force is pulling straight up and down, but just look at how the metal fails. It shears off at a really clean angle. Now, this seems to completely defy logic, but trust me, understanding why this happens is the key to everything.
All right, so our first stop is to really dig into this puzzling diagonal bend. What invisible force could possibly be at play here? You know, the answer isn't some super complex, mind-bending physics equation. It's actually a beautifully simple principle. And once you get it, I promise you'll never look at a piece of steel or aluminum or titanium the same way ever again. So what is this simple principle? To find it, we need to zoom in. I mean, way in. The secret isn't on the surface. It's happening deep inside the metal, right down at the level of individual atoms. Okay, here's the absolute core of it. When we bend a metal, we're not actually stretching the bonds between the atoms like you'd stretch a rubber band. What's really happening is that entire planes of atoms are sliding past one another, kind of like cards sliding in a deck. And look, this isn't just some fun science fact. Understanding and, more importantly, controlling this atomic slide is absolutely critical for modern engineering. It is how we design cars that crumple just right to absorb an impact and protect you, and it's how we build aircraft that can withstand incredible stress without failing.
So, if these atoms are sliding around, what are the rules of the road? What governs this, let's call it, atomic highway? So here's rule number 1, and it's a little counterintuitive. Get this. The more tightly atoms are packed within a single layer, the more space there is between the different layers. Think about it like trying to slide 2 sheets of rough sandpaper against each other versus 2 smooth sheets of glass. That extra space between the atomic layers is like the glass. It creates way less friction, making it much easier for them to slide past one another.
Okay, that makes sense, but it kind of brings us right back to our original question. If we're pulling perfectly straight, where's this sideways sliding force even coming from? Let's use a quick analogy. Imagine you're trying to move a really heavy desk. If you push straight down on it, you're just pinning it to the floor, right? Nothing happens. But if you push at an angle, some of that force you're applying goes sideways, and suddenly the desk starts to slide. The direction of the force is everything. And that's exactly what's happening inside the metal. A straight vertical pull isn't just one single force. It can be broken down or resolved into different components. And one of those components is a diagonal shearing force that acts right along these atomic planes. This hidden force has a name. It's called the resolved shear stress. Now, this isn't just guesswork. There's a whole rule book for it called Schmidt's Law. It's a formula that lets us calculate the exact amount of that hidden sliding force, all based on the angle of the pull and the angle of the atomic plane. The answer it gives you is called the Schmidt factor, and the rule is simple. A higher number means you're getting more sliding force, and the metal's going to deform more easily.
But atoms won't just slide for any tiny amount of force. They resist, they push back. Every single material has a specific threshold, a tipping point, called the critical resolved shear stress. And as soon as the sliding force from your pull gets bigger than this critical value, boom, the atomic layers give away and the metal bends for good.
So, now that we have the rules of the road, let's check out why they make different metals behave in completely different ways. This is where that atomic highway metaphor really comes to life. You see, different metals have totally different road systems. Look at aluminum on the left. Its atomic structure creates 12 wide straight highways. It's like a perfect city grid, making it super easy for atoms to slide. That's why aluminum is so easy to shape. But then look at iron. It's got 48 highways, but they're more like winding country roads. It's way harder for the atoms to slide, and that resistance is what gives iron its legendary toughness. And then you've got metals like titanium. Their atomic structure is like a city with almost no highways at all. This makes it incredibly difficult for those atoms to slide, which is why titanium is just so strong. But there's a really important trade-off. When the pressure builds up, the atoms have no easy escape routes. So instead of bending, the material is more likely to just snap. And that's the crucial difference between being strong and being brittle.
Okay, let's bring all of this together. How does this deep atomic level knowledge actually save lives out in the real world?
This right here is where it all pays off. Take a look at the crumple zone of a modern car. Engineers use Schmidt's law and this whole idea of critical resolved shear stress to design these metal parts with unbelievable precision. They literally engineer the metal so that in a crash, the atomic layers will slide and fold in a very controlled, predictable way, and in doing so, they absorb the deadly energy of the impact before it ever reaches the people inside.
So if there's one core idea to take away from all this, it's simple, but it is so powerful. When a metal bends, it's not stretching, it's sliding. It's this elegant, diagonal slide of atomic planes, and it's all governed by the simple rules of how atoms are packed and the angle of the force. And all this leaves us with one last, really fascinating question. We've just learned that this atomic sliding is what allows metals to bend into form. So, what if we wanted to create super strong, nearly unbreakable materials? What if we could intentionally create traffic jams on those atomic highways and stop the slide altogether? Well, that sounds like a story for another time.